this 7-bit code, it's used to represent characters, as example, from A, B, C, D in capital into Z, or A, B, C, D into small letter into Z, or 1, or comma, or at, or whatever is symbol. As example, take example, the keyboard keys in the keyboards represent many character, many let me say number or symbols, or how we represent them. You see here, as example, I'm talking here about ASCII. It could be in binary, it could be in hexo. You know there is link between binary and hexo. It doesn't matter. However, now here we represent it. You see, 7-bit code. Okay, so we represent A in one code, B in another code, and so on. Just represent each one of them by its code. When it comes to the code, we understand that this represents its B, C, D, whatever it is, art, hashtag, and so on. Now, ASCII code and data transmission, when inside the computer, okay? By the way, I would like to highlight something, that when I say computer, it doesn't mean the PC, the personal computer. It could be personal computer, it could be, well, it's one of them, one of the application, industrial computer, it could be any type of computers, which mean that we have data, we process it, we store it, we come up with output, okay? Now, if I come to ASCII codes and that transmission, I have a transmitter and I have receiver, and data came here, as you can see, produced. Okay, after the input, the data converted into digits, into using one way or a method, another, as example, ASCII code, and then it's transmit. When it is transmit, we expect errors. Okay, this is expected. Now, ASCII code represent the letters, okay, the characters. These are the 26 codes for AZ capital, AZ small letter, okay. Numbers from 0 to 9, dollar sign, percentage, and so on. Okay, a complete listing of monotext also. Now, transmission of these data susceptible to noise. So expect noise, as I mentioned here. It's affected, so it's have a noise. Okay, and typically we transmit the data using either the rates. We use it 500 kilobyte per second, or 56.6 kilobyte per second. Okay, how we transmit data accurately? Now, one of the way is we use parity code. What is parity code? Parity code, actually, it's formed by concatenating a parity bit P to each code words of C of code. Okay, now it could be odd parity code when the total number is odd, or even parity code when the total number is negative. I will explain with example. Have a look here. This is parity code. These are the information. You can see here, this is the 7 bits. Now, I may ask, what is this? You will say that definitely directly it is ASCII, because 7-bit representation. Okay, now, and with this it will be 8. Okay, now if I add once this one plus this one plus this, what I come up with 3. So this is odd parity. The same thing for here. If I add this one, we add this with this one and this one and this one, 4. Oh, it is even parity. Okay, now parity code example. Okay, have a look. If I want to represent 0x and y, now these are the character. This is 0 and this is x and this is equal. Okay, now ASCII represented here in this way. Okay, 7 digits, right? Let's assume we represent them by these codes. Now, parity code, if it is odd or if it is even. If it is odd, we add here ones. Okay, 1, it will be 3. We add here 0 because already it's 3. You can see here already it's 3 ones, so we add 0. While here it is 4, so we add 1, it will be 5. And the same thing, we go for even. We might try to make it even, either by adding 0 to the left or 1 to the left. You see here, they are 2 even, 4 even, 4 even. Okay, so we make it either a odd parity ASCII code or even parity ASCII code. Now let's go to the storage, binary data storage. Usually binary cell used to store data, okay, individual data. Okay, if we put them together, these binary cells, we come with a register. Imagine it's like a battery. You put them together, you come up with a big store, let me say bank, which is, we call it here register. So binary cell store individual bits, okay, the data, and multiple cells, binary cells, we put them together, we have a register. Now data register can indicate different values. It could be used hexo or binary coded decimal or ASCII. We discussed all of them before. Example of binary cell, you can see here. This is binary cell. Individual numbers are coded here. You can see here in ASCII. This is the 7 bits, and this is, we added here to make it as a parity. Now this is odd or even. You will say this is even because I have 1, 1, 1, 1, 4. They are 4. Now register transfer. You see, I'm taking you sequentially until we reach to the computer, the soul of the computer. Okay. Now register transfer. Actually, data move from register to register, and this will supposed to be access to a digital logic circuit to get it processed, and then it go to the output register, which will be store, which could be signal going somewhere. As example, let's imagine it's a computer. It's a computer, PC, personal computer. Now the input data coming from the keyboard, okay, it's inside, it is get coded, let me say ASCII, parity odd, or even, whatever it is, and it's stored in binary cells or in a register, or let's say more than one binary cells. Then this go to what we call it digital logic circuit, because in the important part of the computer is the process, how we process this data. As example of the process the data, you have 2 registers, each one of them contain number. You enter them to the process, to the digital logic to add them. This is a process. We add them together, subtract them, multiply them. This is a process. And the output going to another register to store the output, or could appear in a 7-segment display, or in a monitor, or whatever it is. Okay. Now transfer of information. Have a look how we transfer the information. Now to transfer first of all, we need the input unit, and then the data will be processed, going to the process unit, and then it's stored in the memory. Have a look at the example. This is my keyboard. I want to write the word John, John. Okay. First of all, it's go to the control here to we produce the code, ASCII, let me say ASCII or parity, odd, even, whatever it is, JOHN, and store each one of them in this register. This is called the input register, 8 cells, and then enter them to the process. The first one, the second one, the third one, the fourth one, we put them together, okay, in this sequence. Now we process them because we are putting them together to produce a word, which is John. Now after that, the process unit is go to the memory unit to store it. You see here, John is stored as a ASCII, let me say, code here, where we add also ones, and because it's 7 digits, we add here the 8 digit to make it either odd or even. You can see as example here, this is the first 7 digit, and we add, so here, from here, and we add here number to make it odd, let me say parity. Okay. Now if we want to build a computer, okay, now see here, let's assume we have operand here 1 and 2. This is already the code for operand here 1 and operand 2, and it get a process. Operand 1 going to this register, and operand 2 going to this register, 2 registers. Then they enter together into digital logic circuit for binary addition, because we want to add them together to produce output. Okay. Now this is the output. Go to register 3. Don't forget, register contain binary cells. Okay. This is the output, the sum. It's go to the memory and we store it here. Done. This is the process. So we need the processing, we need the storage, we need communicating. This is the idea of using digital systems to build a computer. Okay. In the next few topics, we will see how we build logic circuits, logic gates, and how we use it in building a computer or parts of the computer. Now, in summary, in this topic, we cover the tools complement most important. It's found to be most important, and we use it in number codes. Also, we use the ASCII, and we learn how it works, how we represent characters. We discuss the registrar store binary, which is used to store binary data based on binary cells, and then how we process it, and then we will use the ideas discussed in this topic and the last two topics to build logic circuit. Let me stop here. Thank you.